Hello, this is Jim Corkins again, and we're continuing on with rotation. And now we are at 5.4.0 in the rotation in the rotations module, and we're going to be talking about kinetic energy today. So, rotational kinetic energy is another type of kinetic energy in addition to the linear kinetic energy. This is a similar kinetic energy, but it deals only with rotational energy. Okay, just like its counterpart, the linear kinetic energy, which I'll write the equation here just to, again, to familiar yourself with. Linear kinetic energy is 1/2 mv squared, and its units are joules. Well, with rotation, so this is now going to be linear kinetic energy, which is this going to be sub L, which we're going to now designate. Rotational kinetic energy, well, M becomes an I and V becomes an omega. So typically when we're talking about linear kinetic energy, we're talking about the center of mass of the object. And that center of mass is moving, so it's kind of like almost like a point source. But with rotational kinetic energy, we're talking about an object spinning about its center. Okay, and again, its units are in joules. So moving down here, let's familiarize ourselves with rotational kinetic energy. So we're going to do 4 little quick problems. And look at rotational kinetic energy and try to get really into how I and omega and also the parts of the moment of inertia I affect kinetic energy. All right, so here we go. Suppose you have 2 objects. One is a disk and one is a hoop. The disk has a moment of inertia of 1/2 mr squared. The hoop has a moment of inertia of mr squared. And suppose both objects have the same mass and same size. Which one is going to have more kinetic energy? So suppose they're spinning at the same rate. They have the same mass, same size, and same omega. So just based on the moment of inertia, which object is going to have more kinetic energy? So think about the problem and pause the video. Okay, we're back. So let's write out these moments of inertia right here. So a disk or cylinder has a moment of inertia of mr squared, and this hoop has a moment of inertia of mr squared. So the disk is 1/2 mr squared, the hoop is mr squared. Well, rotational kinetic energy, again, rotational kinetic energy for both objects for rotational kinetic energy is basically written as 1/2 I omega squared. K is going to be equal to, so the moment of inertia for this object is going to be 1/2. Well, it's going to be 1/2, and then the moment of inertia is 1/2 m, and I don't like that being lowercase. I think it's more clean to make that capital R. So capital R squared, and this is capital R squared. Anyways, back to the problem. The kinetic energy of the disk or cylinder is going to be 1/2 right here, and then the moment of inertia is going to be 1/2 mr squared and omega squared. The kinetic energy for this hoop is 1/2, and its moment of inertia is mr squared, and its omega is the same omega. They're both just omega squared. So this kinetic energy over here is going to work out to be 1/2 times 1/2, so that's going to be 1/4 mr squared omega squared. This kinetic energy for the hoop is going to work out to be 1/2 mr squared omega squared. So this kinetic energy has twice the kinetic energy of the cylinder. Since the cylinder has a smaller moment of inertia, it's going to have a lower kinetic energy. That's like saying that two objects have the same speed. The one object that has more mass right here is going to have more kinetic energy, regardless, even though they're both moving at the same speed. Okay? So that's what this is that's the analogy. Let's try another one. Here you have, again, you have two objects. You have a disk and another disk, so they have the same moment of inertia. And I'll write that up here. Moment of inertia of both objects, just the basic equation, is going to be 1/2 mr squared. Okay, for both objects. But this object on the left has twice the radius. In fact, I want to write this as 2r and r. It'll make the math look a little bit better. So this has got twice the radius, while this has just got one radius. So 2r and 1r. Both have the same mass and both are spinning at the same rate. Which one is going to have more kinetic energy? Okay, well, let's write the kinetic energy equation. Again, it's going to be 1/2 I omega squared, but this I for this one is going to be 1/2 m, and it's 2r squared. So this is going to be 2r that we're going to be squaring. It's a lot of brackets. Times omega squared. Okay, so let's multiply this out. This is going to be 1/2 times 1/2. That's 1/4. 2r squared is going to be 4r squared, because we're squaring 2 and squaring r, and this is omega squared. So the 1/4 and the 4 are going to cancel each other out. So this is going to work out to be just mr squared omega squared. Okay. Let's take the kinetic energy of the smaller guy right here. This smaller guy, which is just r, and this is, again, 2r. So the smaller guy is going to be 1/2, and its moment of inertia is 1/2 m, and its radius is just r that we're going to square, and this is going to be times omega squared. So k is going to be equal to 1/4 mr squared omega squared. So in this case, this larger object is going to have more kinetic energy than the smaller object. In fact, it's going to have 4 times the kinetic energy of the smaller object. Okay? So that's how radius affects moment of inertia. Radius is affecting moment of inertia and increasing it, and that in turn is increasing the kinetic energy. Let's try another one. Here we're going to have 2 objects, and I like the way I had those laid out. We have 2 objects. They're the same size, so they're same radius, the same mass, and they have the same kinetic energy. And we're going to ask who is spinning faster. So here we're asking about which objects are going to be spinning faster. And just for reference, I've given you the moments of inertia here. So think about the problem and try to answer it, and pause the video. Okay, we're back. So this guy's kinetic energy here. So let's start out really quick and let's just set, since they both have the same kinetic energies, we're going to do the kinetic energy of the disk is compared to the kinetic energy of the hoop. And it says they're equal kinetic energy. Now the disk has, so the disk is 1/2, and its moment of inertia is 1/2 m r squared, and its omega, we're going to subscript it d so we could keep it separate from the hoop's kinetic energy, the hoop's omega. Okay, so on this right hand side, this is going to be 1/4 m r squared omega sub d, should be a d squared. On the right hand side of this is going to be 1/2, but its moment of inertia for the hoop is m r squared, and its omega, we're going to subscript it with an h, and we're going to square that. So this is going to be 1/2 m r squared omega sub h squared. Kind of running out of room here. So is it okay if I erase these little units so I get a little bit more room? So in this problem, some things cancel out. The m's cancel out since they're on both sides. The r squareds cancel out. And then what we have on the left-hand side is 1/2 omega d squared. Oops, that should be 1/4. 1/4 omega d squared. And this is going to be 1/2 omega sub h squared. All right. Let's square root both sides. Square root both sides here. And this is going to be 1 over the square, this will be 1/2. Square root of 1/4 is 1/2. And that's omega d. Make sure that looks a little bit more like an omega. And this is going to be 1 over the square root of 2. Omega sub h. Okay. I'm going to multiply this onto the other side. I'm going to multiply the 2 onto the other side. So omega sub d is going to be equal to omega sub h. That's going to be times 2 over square root of 2. I'm going to turn that into a number so we know what that looks like. Okay. I promise I'll answer the question in a second. So square root of 2 on the bottom is going to be 0.707. I'm going to multiply that by 2, and that's going to be equal to 1.41. Okay. So here's what this is saying. Omega sub d is going to be equal to 1.41 times omega sub h. So basically, omega sub d is going to be spinning much faster than omega sub h. It's going to be spinning equal to omega sub h, but also with an additional 41% more spin. So almost 1.5, omega sub d is going to be spinning almost 1.5 times omega sub h's spin. Okay? So again, the one that has the larger moment of inertia is going to be, in this case, it's going to be spinning slower, right? Another way of conceptually looking at this is 1/2 I omega squared, and let's bring the I down below the K. And now we have a relationship between omega squared and k and I. And since k is pretty much a constant and this is pretty much a constant, we're kind of making an analogy that I is roughly equal to omega sub squared. So in other words, if I goes down, omega is going to go up. That's kind of what we're saying here. And so that certainly is the case from here. Since this has a smaller moment of inertia than this other guy, in fact, it's got half the moment of inertia of the hoop, it's going to be spinning faster. So that was like another way of doing this problem, but just conceptually without doing numbers. Let's do the last part in this series. This is just another really quick problem, and this one is pretty straightforward too. Suppose you have two objects that are the exact same object. They both have the same masses, same size, and so same masses, same size, and since they're both cylinders or disks, they're both going to have the same moment of inertia. So the only difference is this one's going to be spinning half the speed of this other one. All right. So go ahead and pause the video before I do this. Pause the video and think about which one's going to have more kinetic energy. Okay. Same exact size and shape and mass object, but one spinning faster than the other. So pause the video. Okay, we're back. This right-hand side object is going to have a kinetic energy, which is going to be 1/2 mr squared, and it's spinning at just omega that we're squaring. So this kinetic energy is going to be equal to 1/4 mr squared omega squared. The object on the right is also, it's 1/2, and it's also got the same moment of inertia, but it's spinning at 2 omega squared. All right. So this guy's kinetic energy is going to be 1/4 mr squared, but this is 2 squared and omega squared, so that's 4 omega squared. The 4s are going to, 1/4 and 4 are going to cancel each other out, so this is going to be equal to mr squared omega squared. It's kind of like saying 1 mr squared omega squared. At any rate, this, the right-hand side object, because it's spinning faster and that omega is being squared, it's going to really ramp up the kinetic energy. It's going to make the kinetic energy go through the roof. In fact, this is going to be 4 times greater the kinetic energy of the left-hand object. Okay, so I hope you learned about how moment of inertia, mass, radius, and omega interact with kinetic energy and how they all affect each other from these 4 problems. Let's now move to some practical problems. All right. So back in energy, we were doing energy, and we're doing energy bar charts. Okay. And in those energy bar charts, we're looking at how linear kinetic energy, potential energy due to gravity, potential energy due to a spring, work due to a force, work due to a friction, how they related. And we're using energy bar charts to do that. Well, now we're going to be doing the same thing. We're going to be using energy bar charts, but now we're going to be adding an extra type of kinetic energy. Okay? So let's do a problem right here. Suppose you have a hoop and a disc. They have the same radius and same mass, and they're released at the top of an incline at rest, and that incline is a height of 3 meters, and they're released at the same time. And basically the question is asking which one is going to be have a higher velocity at the bottom of the ramp. So go ahead and think about this problem, and feel free to use these energy bar charts. Again, you have two different types of kinetic energy. So we're going to do over here, I'm going to help you a little bit get started. Here is the disk, and its moment of inertia is 1/2 mr squared. Over here, we have a hoop. I'm going to use a different color, and its moment of inertia is mr squared. Now, if you look carefully, it's got two different kinetic energies. It's got a linear kinetic energy and a rotational kinetic energy. So we're going to zoom in, as well as potential energy due to gravity, potential energy of a spring. Again, this is the linear kinetic energy, and this is the rotational kinetic energy. Linear kinetic energy, rotational kinetic energy. Linear kinetic energy, rotational kinetic energy. All right, so this is kind of the setup for the problem. Again, they're both starting at the top of the ramp from rest, and then when they get to the bottom, they're going to be at a height of 0 and be moving. All right, so which one's going to have a higher velocity at the bottom? Try out the problem and let's see how you do. Go ahead and pause the video. Okay, let's go ahead and do this. All right. Since they both have the same mass and same radius, this disk is going to have 1/2 the moment of inertia of the hoop. So my guess is, and we kind of did this problem up here, we found out that the disk right here had, the hoop had twice the kinetic energy, rotational kinetic energy of the disk, which is a cylinder, right? So we know kind of from experience that this hoop is going to have twice the kinetic energy of the disk. So let's go ahead and write that in here right now. In fact, what I'm going to do is I'm going to reserve red for the linear kinetic of the rotational kinetic energy. So I'm going to just modify this real quick so it makes sense. The hoop right here is got a moment of inertia of mr squared. Okay, and we said the rotational kinetic energy of the hoop is probably going to be twice that of the disk. Okay. All right. Well, here we go. So at the top, the disk is not moving. So it has no linear kinetic energy. It has no rotational kinetic energy. And I should probably indicate that here. Rotational kinetic energy with red. It also has there's no springs, and there's not going to be any work, at least initially. So since the disk and the hoop have the same mass, we're going to basically say this. Let's just give them both 2 bars of potential energy. Okay. So in both cases, they're going to have the same initial setup as 2 bars of potential energy due to gravity. Okay. After they finish rolling down the hill, they are both moving linearly, and they're also moving rotationally. But their height is 0, and again, there's no springs. Okay. So at the bottom of the hill, now this is going to get kind of weird. We're not sure what's going to happen, but we do know we're going to have maybe 2 blocks here to play with. So I'm going to say this, it's going to have, actually, let's make this 3 blocks to play with. Let's make them both 3. Again, this is arbitrary, but I'm just doing this to illustrate something that maybe it's going to have 2 blocks of linear kinetic energy and actually 2 blocks of linear kinetic energy and 1 block of rotational kinetic energy here. Well, this other object, the hoop, which we know it's going to have a higher rotational kinetic energy, which I'm going to assume that means it's going to have more rotational kinetic energy by 2 than the disk. Okay. So I'm just guessing at that. I'm not sure. I would rather let the math work it out. But let's go ahead and try using some numbers for this. Okay. Oops. So since we have some numbers, we have the radius and the mass, and they're both at rest at the top, we could go ahead and start building some equations here, right? So just as always, we're going to set the initial energy equal to the final energy. Since there's no work, we don't have to add work into this case. Okay. And the potential energy due to gravity of the disk is right here. And then we have the linear kinetic energy of the disk plus the rotational kinetic energy of the disk. 2 separate energies. Moving along, we have mgh, which is the potential energy due to gravity. Okay. The linear kinetic energy is going to be mv squared. And the rotational kinetic energy is 1/2 I omega squared. We're going to substitute our 1/2 mv squared. We're going to substitute in for I 1/2 mr squared. So it's going to be 1/2 times 1/2 mr squared, and so that's the I for that one, and times omega squared. But if you recall, this is the radial form of the kinetic energy, and omega rad, or the radial form of that kinetic energy, radial form of angular velocity. The angular form, the radial form of that angular velocity is v divided by r. So this is going to be omega squared, which is going to be, we're going to be squaring the v, but also the r. So this is going to be v squared over r squared. Okay. We could substitute some things in here. So we substituted in 1/2 mr squared for I, and since omega here is a radial form of omega, that's going to be v over r, which are both being squared. The great news about doing this is a lot of stuff gets canceled out. Okay, the r squareds are getting canceled out. Since the m is here, here, and here, that is also going to get canceled out. So g times h is equal to 1/2 v squared. This is the velocity at the bottom of the ramp, plus 1/4 v squared, since all of those canceled out. Okay. Putting those two numbers together, might need some room. So let's put these two velocities together. All right. So 1/2 from and 1/4, that's going to be, what is that going to be? 1/2 and 1/4. So we're going to multiply this. So what is that? 3/4 v squared, right? 2/4 plus 1/4, so 3/4 v squared g times h. So we're going to multiply both sides by that fraction. Well, we're going to reverse that fraction and then onto the other side. So that fraction flips, and this is v squared. So when we square root both sides, we get this representation for velocity. Okay. So now when we put in our numbers, let's just say g is going to be equal to 10 meters per second squared. Actually, no, let's just keep it as 9.8 to be consistent with the textbook. Sorry about that. So this is going to be 4/3 times 9.8 meters per second squared times 3 meters. So that 3 is going to cancel out with that 3. So this is going to be 4 times 9.8 equals 39.2. Square root both of those. 6.26 meters per second at the bottom of the ramp. Okay. So the disk is going to be moving at 6.26 meters per second at the bottom of the ramp. Well, here we have the velocity, we have the energy of the hoop right here. And again, we're going to set, since there's no works, the initial energy is going to be equal to the final energy. This is going to be U sub g plus the linear kinetic energy here plus the rotational kinetic energy. Potential energy due to gravity is going to be equal to mgh. The linear kinetic energy is 1/2 mv squared. Again, they both have the same masses. So mv squared. And the rotational kinetic energy is going to be 1/2 times the moment of inertia for this times omega squared. So mgh equals 1/2 mv squared plus 1/2 I here is going to be mr squared. And just like over here, this omega, which is the radial form of omega, is going to, that omega squared is going to be v squared over r squared. Okay. And just like the other problems, the r squareds are going to cancel each other out, and the m's are going to cancel each other out. So on the left-hand side, we're going to have g times h. On the right-hand side, it's going to be 1/2 v squared plus 1/2 v squared. Okay. G times h is going to be equal to v squared. So square root both sides. And so we're going to get square root of g times h is going to be equal to v. And so this is going to be square root of 9.8 meters per second squared times the height, which is 3 meters. So that's going to work out to be 9.8 times 3. And then we're going to square root that. Whoa, I squared it. I meant to square root it. So let's square root it, and that's going to be 5.42 meters per second. Okay. Let me just make sure that I didn't like that. 9.8. Oop. 0.8 equals, and square root. Yep, 5.42. So here's what this is saying. What this is saying is this, is that the disk is going to not only get to the bottom of the ramp quicker, but it's also going to be moving faster at the bottom of the ramp, and that speed will be 6.26 meters per second. While the hoop is going to be moving at the bottom of the ramp, its velocity is going to be 5.42 meters per second. Okay? So that's the basics of how to use the energy bar charts for this. Okay? Moving into another problem, this problem which is the speed of a rotating rod. So there's a hinge right here, and you have maybe it's kind of like a lid or something. So it's like a little lid, and here's the hinge right here. I went and I grabbed a energy bar chart because I thought I forgot to attach it to this problem. So there's a little hinge here. So they're saying that this has got a mass. If we look here, it's got a mass. The bar has a mass of 0.2 kilograms. It starts out not moving, and its center of mass is a distance, is this distance from here to here. So that's actually the length of the bar, which is 1 meter. So everything, when we're going to be analyzing this information, the potential energy due to gravity is going to be relative to the center of mass of the bar. All right. So here's the information. It's going to swing down here, and it's going to swing down such that the center of mass is now right here. So that center of mass is about 1/2 L above the ground. And we want to know what speed it's coming in and it's going to be hitting this wall. What is its speed right before it hits this wall? So at the top, it's not moving, or it's not moving or rotating, and it's got a height. The center of mass has a height of L above the ground. At the bottom, it's swinging down, and so it's got a linear velocity, but it's also it doesn't have a linear velocity. I'm so sorry. It's got a rotational velocity. Linear velocity means the entire system would be moving. So here it's rotated down and it's moving at some final velocity. All right, and the center of mass is a height 1/2 L. So go ahead and think about the problem. Use the energy bar chart that I've given you over here, and go ahead and solve it. And take a shot. Go ahead and pause the video and try it out. All right. Well, I'm going to use the energy bar chart. As stated earlier, it's not moving or rotating in the beginning, and it has no springs or outside work acting on it. So I'm going to give this 2 chunks of energy. 2 chunks of potential energy due to gravity. Later on at the bottom, so the center of mass is here, right here, and that's this. And in fact, let me give this 3 chunks of potential energy due to gravity. Okay. Now, when it swings down here, the center of mass now, it was height L above here. The center of mass now is going to, actually I should have given this an even number. Why don't we go with 4? When it swings down here, now the center of mass is only a distance 1/2 L above. So it's going to have half the potential energy due to gravity. Again, it's not moving linearly and there's no springs, but it is moving rotationally. So since the height has dropped in half, the center of mass is a distance L, and now the center of mass is distance 1/2 L, that potential energy due to gravity is going to be half the original potential energy due to gravity, and that means the other two blocks had to hop onto the rotational. Okay. So we're going to solve this just the way we solved the other problems. We're going to set the initial energy equal to the final energy. So the energy is conserved. There's no outside works. Potential energy due to gravity initial. That's going to be equal to the rotational kinetic energy plus the potential energy due to gravity in the very end. Okay. Now I'm doing this a little bit differently than the book does. I'm not sure the math that they're doing here and why there's a negative, but I like the way I'm doing this. So potential energy due to gravity is going to be mg, and again, the center of mass is a distance L above the ground. So that height is going to be the length L. The kinetic energy, rotational kinetic energy, is 1/2 I omega squared, and we'll take care of that in a second. Okay. Plus, in the end, it's also mg, but the center of mass is now half the length above the ground. So L over 2. Okay. mgl is going to be equal to 1/2. The moment of inertia for a rod spinning about one of its ends is 1/3 ml squared. That's the moment of inertia times omega squared. And in fact, omega, we should probably rewrite that right now. That omega here can actually be rewritten. It said here in the problem, the velocity is equal to omega L. Really what that is saying is that omega rad is equal to the linear velocity divided by the size of the object, right? That's kind of what that's saying. So here, omega, which is velocity divided by the length, is going to be, but it's being squared, is going to be the velocity squared divided by the length squared, plus mgl over 2. All right. So a lot of stuff is going to get eliminated. The m's, first off, are going to get eliminated. These L squareds are going to get eliminated. Okay. And so what we're going to have over here is going to be G times L, and this is 1/2 times 1/3, so that's going to be 1/6, and this is V squared, okay, plus GL over 2. Okay. So I'm going to bring this onto the other side. I'm going to subtract this over. When I do, basically what we're going to have is, let me go ahead and give myself some room. I'm going to bring this, when I subtract that onto the other side, I'll have GL minus GL over 2. If we pull out a GL there, we're going to get GL minus 1/2, which is going to be GL divided by 2. All right, so that's on the left-hand side. On the right-hand side, we just still have the 1/6 V squared. 1/6v squared, and 1/6v squared. So now I'm going to multiply both sides by 6. 6gl divided by 2 equals v squared. This is going to be 3gl equals v squared. So the square root of 3gl is going to be equal to v. All right. So the length of the rod is a length 1 meter. So this is going to be 3 times 9.8 meters per second squared times the length L, which is 1 meter. So this is going to be 3 times 9.8. 3 times 9.8 equals times 1 meter, so 29.4, square root 5.42. That seems to be a common theme. 5.42 meters per second. So that's how fast that rod is going to be hitting that wall when it swings down. Okay. If you notice, I did it a little bit differently than our books. I like my way a little bit better. It's a little bit more intuitive. I understand why they're actually making that center of mass negative, because it's actually dropping down below the 0 mark, but it's dropping down below the center of mass of 0. So it's dropping down a length negative 1/2 L. I set my bottom here to be 0. They set theirs up here to be 0. So anyways, I like this better. This makes more sense to me. But I hope you enjoyed this part of the kinetic energy. The next part that we're going to move on to is momentum. Thank you very much.